Chandrasekhar, who was an Indian graduate student, set sail for England to study at Cambridge. During his voyage from India, Chandrasekhar worked out how a big star could be and still separate itself against its own gravity after it had used up all its fuel. This makes them move away from each other and so tends to make the star expand. A star can therefore maintain itself at a constant radius by a balance between the attraction of gravity and the repulsion that arises from the conclusion principle. Just as earlier in its life, the gravity was balanced by the heat. Chandrasekhar realized, however, that there is a limit to the repulsion that the exclusion principle can provide. The theory of relativity limits the maximum difference in the velocities of the matter particles in the star to the speed of light. This meant that when the star got sufficient dense, the repulsion caused by the exclusion principle would be less than the attraction of gravity. Chandrasekhar calculated that a scorched star of more than about 1.5 times mass of the sun would not be able to support itself against its own gravity. This is called the Chandrasekhar limit. This had serious implications for the ultimate fate of the massive stars. If a star's mass is less than the Chandrasekhar's limit, it can eventually stop contracting and settle down to a possible final stage as a white dwarf. With a radius of a few thousand miles and the density of hundreds of tons per cubic inch, a white dwarf is supported by the exclusion principle repulsion between the electrons in its matter. We observe a large number of these white dwarf stars. One of its first to be discovered is the star that is orbiting around the Sirius, the brightest star in the night sky. It was also realized that there was another possible final stage for a star also with a limiting mass of about 1 or 2 times the mass of the Sun, but much smaller than even the white dwarf. These stars would be supported by the conclusion principle repulsion between the neutrons and protons rather than between the electrons. They therefore called neutron stars. They would have had a radius of only 10 miles or so and a density of hundreds of millions of tons per cubic inch. At the time they were first predicted, there was no that neutron stars could have been observed, and they were not detected until much later.